Hello everyone, thanks for checking out my video on topic 7.8 today. This is the last topic in our 7th unit in Calculus AB. Topic's name today is called Exponential Models with Differential Equations. Okay, so we're going to continue on with our differential equations, but now we're going to basically look at exponential functions and where they come from. So as reading here, oftentimes physical phenomena can be described by a differential equation. For example, problems involving radioactive decay, population growth, and Newton's law of cooling can be formulated in terms of an equation that contain a derivative or rate of change. Growth and decay. Let's start with that here. In many applications, the rate of change of the variable y is directly proportional. We've talked about that before, directly proportional to the value of y. So when we see directly proportional, we have some type of k constant times y. If y is a function of t, the proportion can be written as dy dt equals k times y. The general solution of this differential equation is given by the following theorem, exponential growth and decay model theorem. So if that same thing we just talked about happens, then this is called our general solution to this differential equation. C is your initial value, k is the proportionality constant. Growth occurs when k is greater than 0, and exponential decay occurs when k is less than 0. So let's just go through a quick proof of that. Not that you don't believe me, but just to make sure. There's our differential equation. If we separate our variables, we have 1 over y dy equals k dt. That's natural log of y equals kt plus c. Get used to solving a lot of problems in this section that look like that. All right, so our next thing we're going to do is we're going to change this from logarithmic form into exponential form. The base here is e, so that becomes our new base. This whole right side becomes our exponent, equals y. Now we don't have to have the absolute value bars around y anymore because this is always going to be, y is always going to be a positive number anyway if we're looking at something like this, but also we're not taking a log of it anymore. So it doesn't need to be positive. If it's 0, that's fine. If it's negative, that's fine. Okay, I'm just going to switch the sides here. I like it better when my y is on the left side. All right, and then hopefully you remember in Algebra 1 theorem that allows us to do this. If you have, let's say, for example, x to the 2 plus 3, that can be written as x squared times x cubed. Now, you probably did it more the other way. If you had this, you did this. But it does go both ways. So I can rewrite what I have here as e to the kt times e to the c. E is a constant, C is a constant. When you raise a constant to a constant, you get another constant. So instead of writing that as e to the c, we just write that as some constant c. And if I bring that out in front, I get y equals ce to the kt, which is what we have right there. Like I said, get ready to do that a lot in this section. Example 1, the rate of change of y is proportional to y. Remember, if it doesn't say directly proportional to y or inversely proportional to y, we know it means directly. So that tells us here the rate of change of y is directly proportional to y. When t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? Okay, so our first thing we need to do would be to solve this for y, but we just did that. So let's go ahead and use the equation we just proved. Now we have 2 points. If one of them gives you 0, the initial condition here, that's great. Always start with that point. Okay, if neither of them give you 0, we can talk about what to do with that later. But for now, luckily we have a point that's 0, 2. Let's put that in where it belongs. 2 equals ce to the k times 0. E to the 0 is just 1, so 2 equals c. So my equation now is y equals 2e to the kt. Now we can use this point to find our k value. So 4 equals 2e to the k times 2. 2 equals e to the 2k. To solve this, we're going to need to change this from exponential to logarithmic. So it's going to be ln2 equals 2k. or 1/2 ln 2 equals k. Or if you prefer to write that as ln root 2, that is okay as well. All right, so now let's take what we have for c and what we have for k and put that back into our equation. So we have y equals 2e to the 1/2 ln 2 t. So this is now our equation that we can use for any other t values other than 0 and 2 to find the new y value. The question says, what is the value of y when t is 3? So we'll put 3 in there. So it's going to be 3/2 ln 2. All right, we can simplify this down here a little bit. E to the 3/2 ln 2, we can write that as e to the ln 2 to the 3/2, right? And then e to the ln power would cancel out. So we're left with 2 times 2 to the 3/2, which we can write as 2 to the 5/2. And that's our final answer. The point would be 3 comma, 2 to the 5/2. Great. Here's some applications of growth and decay. You probably remember some of these from your pre-calc course last year. We're going to take a slightly different approach with these problems now that we have a formal growth decay model with which to work, and we know where it comes from. We work on the assumption that the rate of decay is directly proportional to the amount of material that we start with. So here's some half-lives of 6 basic isotopes. The one we talked about a lot in pre-calc is carbon, because many life forms on Earth are carbon-based, but we have a couple others that you can take a look at as well. All right, number 2. Suppose 15 grams of the cesium isotope CS-137 that was released during 1986 Chernobyl nuclear accident and absorbed into the groundwater. How long will it take for 15 grams to decay to 1 gram and become safer to drink? Okay, let's start with our exponential growth and decay model that we already have proven earlier. I'm not going to call it y, though. I'm going to call it a. Actually, I'm going to call it a of t for an amount. You can call it whatever you want, but a for amount sounds good to me. Okay, and there's our model that we have. Let's read through the problem here. We see 15 grams is what we start with. So the point 0, 15 is the point that we know for sure. Okay, let's start with that. If we put 15 in here, we get CE to the K times 0. So 15 equals C. So now I have A of T equals 15 E to the KT. Okay, so now we can look back at, where is it here? Cesium is 30 years, right? So after 30 years, half of that would be left, 7.5. We can use that to find K. 7.5 equals 15 e to the 30k. So 1/2 equals e to the 30k. And really, we don't even need this. If it's half-life, we know that the amount's going to be half of the original amount, and that k value, that t value would be 30. All right, so solving this for k, we would get ln 1/2 equals 30k, and then 1/30th ln 1/2 equals k. So now our function is 15 e to the t over 30 ln 1/2. And it says how long will it take for the 15 grams to decay to 1 gram. So we want to know, when will A be 1? So 1 equals 15 e to the t over 30 ln 1/2. So that'd be 1/15 equals e to, I'm going to rewrite this as ln 1/2 to the t over 30. So the e to the ln will cancel each other out. We're left with 1/15 equals 1/2 to the t over 30. Yeah, we just got rid of that ln, but now we're going to use an ln again. Well, you can use any log base at this point, but the two that we use in the calculator are ln and log base 10. Those are the easiest one to use. So I would suggest using ln or log base 10. Let's take that on both sides. So I'm going to do ln of 1/15. And on the right side, I'm going to do that same thing. You have to, but I'm also going to take the t over 30 out in front. Remember, you can always take an exponent out in front. Oops, I put 1/15, I meant 1/2. Okay, so then solving for t, what we got to do is we got to multiply by 30 and divide by ln 1/2. So 30 ln 1/15 over ln 1/2 is t. We can now type that into our calculator, and what we would get is 117.207 years. Okay, for the purpose of this, it might actually be easier just to type this into our calculator and get what that would be. Let's see what that would be if we type in 30 ln 1/2. So that would be k is approximately negative 20.7944. Okay, but if you're going to do that, you got to go to at least 4 or 5 numbers after the decimal. Otherwise, your final answer might be wrong. That's why a lot of people in the math world like to just keep it exact as long as you can. But if it's easier just to round that right now instead of writing that 1/2 ln 30 out each time, that's okay too. Example 3, a fruit fly population. Absent-minded graduate student at a university is studying a population of fruit flies in a biology lab. She works under the premise that this experimental population of fruit flies increases according to the law of exponential growth. She counts 100 flies after the second day of experiment and 300 after the fourth day. However, she forgot to record the number of fruit flies she initially had at the beginning of the experiment. So we talked about this earlier. What if we don't have an initial condition? That's what we're going to look at here. This one's going to be a little bit more difficult to do. Okay, so we know our equation is y, or in this case, again, a of t. I'm just using a for amount, equals c e to the kt. That's our exponential growth or decay model. We have 2 points. 100 flies after the second day. So 100 flies on the second day, and 300 flies on the fourth day. So 300 flies on the fourth day. Now, it doesn't look like one that you did in Algebra 1, but this is just a set of 2 different equations with 2 different variables, right? So some of the ways you probably learned how to solve these systems of equations back in Algebra 1 are elimination or substitution or graphing. The best way to do something like this, in my opinion, would be to use substitution. To solve one of these for c or k, or both of them for c, and then we can substitute it in and solve for the other variable. All right, so the way I would do this problem is I would solve, let's say this one for c, and that would be c equals 100 over e to the 2k. And then I would put that here. So 300 equals 100 e to the 2k, e to the 4k. If I divide both sides by 100, I get 3 equals e to the 4k over e to the 2k. And remember, if you have things with like bases, we subtract the exponents. So it would be 3 equals e to the 2k. Taking the log of both sides, use natural log. So natural log of 3 equals 2k. And 1/2 ln 3 equals k. So I'm going to do what I said on the last one there. And I'm going to round this right now, and you can see if you think this is easier. So K is approximately 0.549306. I would write down as many numbers as you can there to make sure that we don't miss anything along the way. So the question now says, well, actually, before we do the question, let's write down our equation now. So A of t equals C e to the 0.549306t. Or you can write down half ln 3t. Okay, now the question says approximately how many flies were in the original population. Okay, so we want to solve for our original amount. Okay, so if we put 0 in for this, now we should be able to figure this out. But if you look at it right now, we actually have 3 variables, and that's not good. So what we can do is we can replace C with what we have right here for C, since we know what K is. And then we only have 2 variables. And then we're going to put T equals 0 in because we want initial amount. So that gives me A of T equals 100 over 2 times, e to the 2 times 0.549306 times e to the 0.549306 times 0. Okay, so this will all just be 1. So I really don't need that. So really all we're looking at here is that right there. And if we type that into our calculator, this should be A of 0. We should get about 33.333. It says round to the nearest fly, so that would be 33 fruit flies. All right, example 4. 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. The sales follow an exponential pattern of decline. What will they be to the nearest unit after another 2 months? All right, so this one's a little bit easier. Again, we have our initial, which is 100,000. And then we have our second point, which is 4 months, 80,000. And then it says if the sales follow this pattern, what will they be after another 2 months? So when t equals 6. So we're going to go through this one pretty quickly here, since it's our third one. All right, using the point 0, 100,000, we would get that C is 100,000. Using the point 4, 80,000, we would get 0.8 equals e to the 4k, and then ln 0.8 equals 4k, and then ln 0.8 over 4 equals k. And I'm going to use a decimal again for this. So k is negative 0.0557858878. So actually it's 6 there. So now our equation is A of t equals 100,000 e to the negative 0.055786t. All we're going to do now is put 6 in for t. Type that in our calculator, and we should get 71,554.175 units. But it says to the nearest unit, so that would be about 71,554 units. All right, the coolest part about this section, in my opinion, is called Newton's Law of Cooling. Newton's law of cooling states the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. What this basically means is if you take something that's really hot and bring it into a cold room, how long will it take to get the room temperature? Okay, now it's also vice versa. If you take something really cold and bring it into a warm room, how long will it take to get to room temperature? T equals 0 represents the temperature of the object. Sorry, T sub 0. T sub E represents the temperature of the surrounding environment. Newton's law of cooling is not specifically tested in the AP exam, just so we know, although models that closely resemble it sometimes are. So it's a good thing just to get some practice in with this. All right, number 5, the world-famous pastry chef Bernie D. Rolls removes a completely baked cake from an oven and places it in a cooling rack in a room whose temperature is kept at 60 degrees. Using a cooking thermometer, he determines the cake cools from 100 to 90 in 10 minutes. The icing that is used for the cake cannot be applied until the cake's temperature reaches 80. How long must Bernie wait to ice the cake? All right, let's start with Newton's law of cooling up here. So d T0 dt, little t would be time, equals k times, and then the rest of it would be T sub 0 minus T sub E. Remember, T sub E is the temperature of the surrounding room. We know that already. We know that's 60, okay? So we can go replace that with 60. All right. Now we're going to use some of what we learned last chapter and this chapter combined, starting by separating our variables, big T and little t, and then taking the antiderivatives of both sides from there. Now remember, the left side, that's going to be a logarithmic antiderivative, but because the derivative of the denominator is 1, we don't really need to go through the whole process of substitution. It's going to be ln absolute value T0 minus 60. Over here we have kt plus c. But wow, that's a lot of variables. A lot of variables in there, right? All right, so now we can put in our initial condition. He took it out at 100 degrees Fahrenheit. So when little t is 0, initial condition is 100. So ln of 40 is c. Okay, now I can rewrite my equation as ln T sub 0 minus 60 equals kt plus ln of 40. All right, now we got to solve this for k. We have the second point, which is 10 comma 90. So ln of 30, because 90 minus 60, equals 10k plus ln 40. So ln 30 minus ln 40 equals 10k. ln 3/4, if you do some simplifying there, equals 10k. And 1/10 ln 3/4 would be k. Again, now at this point, if you want to keep that as that fraction, that's fine. If you prefer to make this a decimal, which is what I'm going to do here, that's fine. K is negative 0.028768. So now my equation becomes ln T sub 0 minus 60 equals negative 0.028768 T plus ln 40. And now we got to solve this for T. So first of all, changing from logarithmic to exponential form, I'm going to drop the little subscript there. I'm just going to make it as T. And we have e to this whole power. It's a lot there. If we add 60 over, we get T equals this whole thing plus 60. And this is our equation for T, big T, at any time little t. All right, so now all we're going to do is we're going to set big T equal to 80. and solve this. And I'm running out of room quickly here. Let's go back up here now. Subtract 60 from both sides. We get 20 equals e to the negative 0.028768t plus ln 40. All right, we could break that up into 2, and that would be 40 e to that power. Divided by 40, we get 1/2. And of course, my stylus is dying here. So we get 1/2 equals e to that whole power. ln both sides. And divide by that k number. Sorry, I'm really running out of room over here. And you get 24.094 minutes. But he's already waited 10 minutes. So we can subtract, and what we get is 14.094 more minutes that he has to wait before he can ice that cake. Man, that's a lot of work there. But can't wait to ice that cake in 14 minutes. All right, we got one more problem to take a look at in this section here. Fish are being introduced to a man-made lake. The change in the rate of fish f with respect to time t is directly proportional to 900 minus f, where t is measured in years. When t equals 0, there are 400 fish in a lake, and 3 years later, there are 600 fish in a lake. All right, so let's start with our differential equation. So it would be df dt equals k, directly proportional, so 900 minus f. So that would be 1 over 900 minus f df equals k dt. Taking the antiderivatives, we would get negative natural log 900 minus f equals kt plus c. Using the point 0,400, we would get negative natural log of 500 equals c. So now my equation becomes negative natural log 900 minus f equals kt minus ln 500. If we divide through by a negative sign, might as well make this positive everywhere we can. We get ln 900 minus f equals ln 500 minus kt. All right, now let's use the second point that we know, which is 3, 600. So ln 300 equals ln 500 minus 3k. Subtract ln 500 and combine, we get ln of 3/5 equals negative 3k. Divide by negative 3. So ln of 3/5 divided by negative 3. K is approximately 0.170275. So now our equation is ln 900 minus f equals ln 500 minus 0.170275 t. And that's what we got to solve for f. So 900 minus f equals e to the ln 500 minus kt. If we split that and simplify, we get 900 minus f equals 500, because e to the ln 500 would be just 500. And then e to the negative 0.170275 t. And if we solve that for f by adding and subtracting both sides, we would get f, which we can call f of t, equals 900 minus 500 e to the negative 0.170275 t. Find the fish population in another 3 years. So that's when t equals 6. So f of 6, just take that and put that right into your calculator. We should get about 720 fish. Find a limit as t approaches infinity of f of t, and explain what the answer means. So if we take a limit as this approaches infinity, okay, really that second part's just going to go to 0. So this is going to be 900. And what does that mean? That's the maximum amount of fish that could be in the lake at any time. Finally, that's it for today's lesson and this unit. Thank you so much for checking this out. Have a great day.